PlanetScale stream video through PostgreSQL, and SpacetimeDB did it before them. And I built in Go, multi-participant, WAL native, and purely running on Kubernetes environment. Every audio and video chunks goes through PostgreSQL's write-ahead log. The WAL is the event bus here. No media server, no WebRTC. Let me show you the architecture, and then we will go through every line of code. And hey, welcome to Hussein Codes. Let's compile. Each browser tab opens a camera, sends Muxed WebM chunks over WebSocket. The Go server writes them to the primary. A single WAL logical replication subscriber on the replica picks up every insert, decodes the tuple, and broadcasts to all viewer WebSockets. No DB reads in the hotbed. Init segments are cached in memory. Late joiners get cached init segments, then leave WAL chunks. That's the entire data flow. Let's look at the code. Two tables, streams, one row per recording session, media chunks, one row per WebM chunk with stream ID, room ID, participant name, seconds, MIME type, and chunk data as byte here. The unique stream ID constraint prevents duplicate chunks with a string. A do block creates the media publication if it does not exist. This publication covers only media chunks, the table whose WAL events we fan out. Quick note here, this runs in Go at startup because CloudNativePG's post-init SQL does not support $quote, but the publication is also created during CMPG Bootstrap for fresh clusters. Here, CloudNativePG is the operator for Postgre in Kubernetes environment. We will also manage our PostgreSQL cluster by using CloudNativePG. The hub is an in-memory viewer registry keyed by room ID. It has two maps: viewers, all connected viewers WebSocket per room, and init segs, the cached seconds 0 JSON payload per participant per room. When the WAL subscriber sees a chunk with sequence 0, it caches the serialized payload here. This is the WebM initialization segment, the codec header. Without it, a source buffer can't decode anything. When a new viewer connects, we send all cached init segments immediately, no database query. Broadcast fans out a payload to every viewer in a room. Non-blocking send with a select default. If a viewer's channel is full, we drop the message instead of blocking the WAL subscriber. The participant registry tracks active recorder names per room. When a recorder joins, we add their name. When they disconnect, we remove it and broadcast the updated list. This drives the grid tiles in the browser. The subscriber is wrapped in a retry loop. If the replication connection drops, it retries in 3 seconds. This is the core. We open a replication connection to the replica. Replication is equal to database in the DSN. This is a special PostgreSQL wire protocol mode. We drop any existing slot, then create a fresh temporary one. Temporary slots auto-drop when the connection closes. We drop any existing slot, then create a fresh temporary one. Temporary slots auto-drop when the connection closes. No stale slots accumulating behind the WAL. We start streaming from the current WAL position. We only care about live changes. Start replication with proto version 1 and the publication names MediaPub. From here, every committed insert on media chunks arrives as a WAL event. Two message types. Primary keep alive message. We respond with a standby status every 10 seconds. Xlog data, actual WAL data passed to handle WAL message. In handle WAL message, relation message gives us column schema cached by OID. Insert the message is what we care about. We decode the tuple into a Go map, build an outbound chunk, and if second is equal to 0, cache it as the init segment. Then broadcast to the room. This is the key line. Every time the recorder restarts and produces a fresh seconds is equal to 0, the cache updates. Late joining viewers always get a recent init segment. When a recorder connects, create a streams row, register the participant, broadcast the updated participant list. Then loop reading chunks and inserting them to the primary. No broadcast here, the WAL subscriber handles that. The recorder periodically restarts its MediaRecorder to produce fresh init segments. When it does, it sends type restart. The server creates a new streams row, so the new second is equal to 0 doesn't conflict with the old streams second is equal to 0 and returns the new stream ID. The WebSocket stays open, the participant stays registered, no flicker. On disconnect, a single deferred closure removes the participant, clears the init segment cache, and broadcasts the updated list. The order matters here. The closure runs atomically, so viewers never see a stale participant list. Viewer handler, register in the hub, send the participant list, send all cached init segments, then loop forwarding messages from the hub's channel. Zero database queries here. Everything is in memory or comes from WAL. Restart the MediaRecorder every 30 chunks to produce a fresh init segment. Each remote participant gets their own pipeline, a DOM tile, a video element, a media source, a source buffer, and an append queue, created lazily on first chunk or participant list update. Init media source creates a media source, wires it to the video via create object URL. On source open via the source buffer with mod is equal to seconds, this tells the browser to ignore embedded WebM timestamps and play chunks in append order. This is critical. Without sequence mode, timestamp discontinuities between recorder restarts would stall playback. This is where the recorder restart magic lands on the viewer side. When we receive a sequence is equal to 0 for an existing pipeline, it means the recorder restarted. We call init media source to tear down the old pipeline and rebuild it fresh. The new init segment is queued and will be appended once the new source buffer opens. No timestamp conflict. Video keeps playing. The recorder side, after 30 chunks, we stop the media recorder, wait 100 milliseconds, send a restart message to the server, and spin up a fresh recorder. The WebSocket stays open the entire time. The participant never disappears. The grid autoscales. One participant is equal to one column, 2, 4 is equal to 2, 5, 9 is equal to 3, up to 8 columns for 50 plus participants. One CSS custom property. When the server sends a participant list, we reconcile, create pipelines for new participants, remove departed ones, play a join sound for new arrivals. This was the code base. Let's jump into the infrastructure part. The whole stack runs in a kind cluster with 3 nodes locally. Setup SH does everything in 10 steps. Kind cluster, Kubernetes stack for monitoring, CloudNativePG operator for Postgres cluster, namespace plus secrets, PostgreSQL cluster, Postgres exporter for metrics, Grafana dashboard for visualization, build plus load Docker image, deploy server, port forward. That's it. Because once we deploy everything in Kubernetes, we will be using port forward to access our application. Cluster resource is coming from CloudNativePG. We are using PostgreSQL 17 and we also enable WAL level. It is logical. This is used on the replication side. Grafana dashboard CMPG is used for visualizing the PostgreSQL statistics. PostgreSQL statistics are exposed by using Postgres exporter. Also, this deployment is for our application. As you can see, we have PG meet server. This is our Docker image. We will be built and load into the kind cluster. And as you can see, we have database URL and replica URL. The write operations will be done against primary. Read operation will be done against replica instance. This is kind cluster setup. We have only one control plane and we have 2 worker nodes. And that's it. Let's run our demo. Now this is creating a kind cluster. This is a local Kubernetes cluster. Now it's installing Kubernetes stack, which is used for monitoring. It contains Prometheus, Alert Manager, Grafana, some kind of useful node exporters. The monitoring stack is installed. Now it is time to deploy CloudNativePG operator. Okay, cluster is also installed. Now it is setting up its exporters. The Postgres cluster is created. Now it is waiting for everything to be ready. Okay, the cluster is also ready now. It is deploying the Postgres exporter. Postgres exporter will collect metrics from PostgreSQL cluster and we will use that Prometheus endpoint for our Grafana dashboard visualization. It is time to build our own image for PG Meet server. This will be our UI, server, everything will be included in this application. That's also installed. Now everything is ready. Now let's open our application. When you open it, just enable microphone and cam. Hi. And here I will join the stream. Now I'm inside stream and our stream name is meeting 1. I will join 20 more participants to this meeting. As you can see, they are joining. Hello. Hello, Mr. Anderson. Video and audio chunks are streamed to the server side. It is stored in PostgreSQL. Of course, there is an overhead for that. If you are interested in how it affects PostgreSQL cluster, you can open Grafana dashboard. In the dashboard, you will see CloudNativePG. When you open it, you will see our database statistics. Let's switch to 15 minutes interval. So what you can see here, you can see the replication lags in real time. You can see the connection trends. You can see the CPU usage, memory usage in history. You can see storage changes, as you can see here, tuple IO, block IO, database size. So it cost us 150 megabytes of data with 10 seconds of streaming in our application. You can see write ahead log statistics. You can see the replication statistics, for example, write lag, flash lag, replay lag. Of course, since this is a local application, 15 milliseconds is expected. But in production environment, especially your primary and replication nodes are in different regions or zones, expect bigger latencies on this part. So that was the demo. I hope you like it. As a recap, browser captures mixed WebM chunks and streams over WebSocket. Go server inserts this data into primary node. A single wall logical replication subscriber takes every insert event and broadcasts them through WebSockets to all the viewers. Do you think is this a production grade conferencing? I don't think so. But it proves that WAL is a legitimate event bus, ordered, durable, and queryable. If you are building recording pipelines, audit systems, or just wanted to understand how replication works, this is a good place to start. Source code is linked below. Like and subscribe for more system engineering content. And see you in the next one.